All right, in the following example here, they give us a degree 3 polynomial, and they want us to show that this polynomial has at least one irrational root. And the key word here is irrational. If we examine the end behaviors of this polynomial, we can quickly see that it has to have a real root. To see this, notice the following. You'll notice here as x approaches positive infinity, I can see my polynomial p at x approaches positive infinity. And likewise, if x approaches negative infinity, we can see our polynomial approaches negative infinity. So visually, we have the following. If you take a look at our Cartesian plane here, I've got a polynomial tending towards positive infinity as x gets large, and then a polynomial tending towards negative infinity as x gets very small. But we know that polynomials are continuous. So I know that in this case here, these polynomials are connected. Again, I don't know the exact structure of the function, but I know it has to look something like this. I've got a y-intercept that's positive, so I try to make it there. But what we do know, because of this, we know that it must cross the x-axis. If it crosses the x-axis, we know that it has a real root. So what we need to show now is that, in fact, it is a real root, but more precisely, that root is irrational. This is where the rational root test comes into play. If you missed the lesson on the rational root test, I will link that in the top right-hand corner. For those of you who've seen it, let's apply the rational root test. So using the rational root test, I know that if my polynomial has a rational root, because the leading coefficient here is 1, it's just going to be factors of the constant term. So therefore, I'm going to look at plus or minus 1 or plus or minus 7. So if my polynomial does have a rational root, it must be one of these 4. So let's go ahead and do synthetic division on these 4 and see if we can get a remainder of 0. And you can see here, I tried synthetic division at 1. I did not get a remainder of 0. I tried at minus 1. I did not get a remainder of 0. Tried at 7. Did not get a remainder of 0. And I tried it at minus 7. I actually didn't even finish calculating. I could see it wasn't going to come out to be 0, so I didn't do it. Didn't continue it. So in this example here, you can see I've gone through all 4 possible rational roots. None of them worked. So therefore, this real root, which we know exists, is not rational. It therefore must be irrational. So this is an example of, by using your end behaviors, you know that the polynomial has a real root. Applying this further, using your rational root test, we can see here if none of them work, that root that this polynomial has must be irrational. Now, it could be the case the polynomial has more irrational roots. That's something we have to talk about later. But in terms of this example here, showing that it has at least one irrational root, just applying your end behaviors and your rational root test will do the trick. Thank you.